Hi everyone, today I'm going to be showing you how to analyze a Stirling cycle using PV, PT, and TV diagrams. It's going to be fun. Let's get started. So the first thing I like to do is to translate English into thermodynamics language. So let's take a look at this state descriptions. So the first one from state 1 to 2 is isotherm compression. Isotherm means delta T is 0. Compression means V, the volume is decreasing. State 2 to 3, isochoric, delta V is 0. Volume doesn't change. Heat addition in this case means T is increasing. Isotherm, so delta T is constant again. And expansion means volume is increasing. Last one, state 4 to 1, isochoric again, so delta V is 0. Heat rejection means T is decreasing. Another important piece of information is the working fluid is air, which tells us, hey, maybe you can use ideal gas law. So that leads us to make our assumptions. All right, so assumptions. So the first one, ideal gas law, or let's make ideal gas as one of our assumptions. If we make this assumption, then we can use PV equals to RT later in our calculations. The second one would be constant mass, since we're dealing with a cycle. Okay? Now we can take a look at all different diagrams. So let's start with PV diagram. So PV diagram. So V on the x-axis and P on the y-axis. Since we're looking at the relationship between the pressure and volume, we can rearrange the ideal gas law equation into P equals to RT divided by V. Here, we can tell that P and V, they're inversely proportional if RT are constant. Okay, let's start with the different states. So from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, so from state 1 to 2, we have, so we're just going to write down this equation again so we can read the descriptions and decide what the graph looks like. So from state 1 to 2, volume is decreasing, temperature is constant, and R is always constant, so P is going to decrease. Actually no, it's going to increase. Sorry. P is going to increase because they're inversely proportional, of course. So that allows us to draw a line from right to left like this. So this is 1 and this is 2. Why from right to left? Because the volume is decreasing. So let me put the arrow on here. Since they're inversely proportional, when V decreases, P is going to increase. So that's why we go up. Now let's go to state 2 to 3. So same equation again. P equals to RT over V. This time, V is constant, but T is increasing. R is also constant. So that gives us the increase in pressure. So since V is constant, it's going to be a straight line. And since the pressure is going up, so it's going to go up instead of going down. Okay, so we're going to have our 3 here. Right, V is constant, so that's going up, a straight line, and P is increasing, so that's why we're going up. So from 3 to 4, same equation, P is equal to RT over V. In this case, temperature is constant, R is constant, but the volume is going up. So volume is increasing, so our pressure is going to decrease. So I'm going to go down like this. So the arrow is pointing this way. Okay. So this is going to be 4. The last one, same equation, RT over V. This time, same thing. The volume is constant, so it's going to be a straight line. But the temperature is decreasing. So RP, pressure, is also going to decrease, which allows us to go down on this curve from 4 to 1. And this also closes our cycle. Right? Now let's take a look at the PT diagram. Now we're looking at the relationship between pressure and temperature. So we're going to rearrange our equation again. So PV equals to RT can be rewritten as P equals to RV times T. So P and T, they are directly proportional. So if we look at state 1 to 2, P equals to RV times T, R over V times T. So state 1 to 2, V is decreasing, T is constant, R is constant, so our P is going to increase. On this diagram, T is constant, so it's going to be a straight line going up because the pressure is increasing. So we have 1, this is 2. This 2 looks terrible. So 2. This color is changed to blue. Sorry. 2. Okay. And from state 2 to 3, same equation, RVT. So this time, V is constant, R is constant, but T is increasing. So P is also increasing. So since they are directly proportional, so we're going to just draw something like this, right? T is increasing, so that goes from left to right. P is increasing, so that goes from the bottom to the top. So now we have 3 here. State 3 to 4, same thing. P is equal to RV times T. In this case, T is constant, so another straight line, but going up or down? Let's decide from looking at the volume change. So volume is increasing, so P is going to, pressure is going to decrease, which makes sense. So here, we're going to draw a straight line going down because T is constant and P is decreasing. So going down here, okay. And then we have 4. The last one is, P is equal to R over V times T. So V is constant, volume doesn't change, however the temperature is decreasing, so the pressure is also decreasing. So we're going to draw a line from 4 to 1, from right to left with pressure decreasing. So something like this. Okay? Oh, I forgot to put the direction of this process. So go from 1 to 2, 2 to 3, 3 to 4, 4 to 1, that closes our cycle. But please pay attention that the slope from 2 to 3 and 4 to 1 is slightly different. That is because the different volume at state 2 and 1. So let's take a closer look at this. So the volume is decreasing from state 1 to 2. So here, if we denote, I'm going to change the color. So if here at 2, we say, hey, the volume at point 2 is V2. That's a smaller volume than V1, right? Because we compress the gas from V1 to V2, okay? So that gives us, so if you look back to our state 2 to 3, actually this P here is going to be V2, right? Because we compress the volume to V2, and then that's how we find the slope of this line from 2 to 3 here. Same thing for process 4 to 1. So from 4 to 1, we have R over V1 as the slope of the line from process 4 to 1, right? Because, so we reduce the volume from V1 to V2 from process 1 to 2, and from 2 to 3, the volume is constant, and from 3 to 4, we increase the volume, we expand the volume from V2 to V1 again. And from 4 to 1, V1 stays the same. Okay, so if you compare these two, since V1 is bigger than V2, so R over V1 is going to be smaller than R over V2. So R over V2 is bigger than R over V1, so that tells us that this slope here is going to be a little steeper than the other one. Okay, which aligns with what I drew here. 2 to 3 is a little steeper than the other one. All right, moving on, let's take a look at TV diagram. So the relationship between T and V. This one is relatively straightforward. We can just read off from our translated thermodynamics language. So if we look at the first state 1 to 2, T is, so let me put the axes first. So we have V and T. So T from state 1 to 2 is constant. So that tells us it's going to be a straight line. But since the volume is decreasing, so we're going to go from right to left. So this is our state 1, this is our state 2. State 2 to 3, the volume is constant this time. So that's telling us it's a vertical line. Since the temperature is increasing, so we're going to go up. Actually, I'm going to move this entire graph a little bit downwards, otherwise I can't fit this in. So let's start with this. So this is state 1, state 2, going from right to left because the volume is decreasing. And now, since the temperature is increasing and volume doesn't change, so a vertical line going up. So this is 3. And from 3 to 4, temperature doesn't change. So it's a horizontal line. Volume is increasing, so it's going to go from the left to the right. So something like this. So this is going to be 4. And the last step is constant volume. So a vertical line again. Temperature decreasing, so it's going to go down. And that also closes our cycle. So this is what the TV diagram looks like. The last question that we want to solve is the change in internal energy. So the change in internal energy of a cycle is equal to the change in internal energy from state 2 to 1 plus state 3 to 2 plus from state 4 to 3 plus the internal energy from state 1 to 4. Since this is a cycle, everything, all the properties of a system return to their original state in a cycle. So the change in internal energy is just 0. Alright? So I hope you think this is a very helpful video, and let me know if you have any questions. Thank you.